Welcome to Physics Hub. Today is 30th December 2018 Sunday, and here I am with a new set video. So this is the last set video of this year, and with this we will complete 240 solved problems. Now as you know that we upload a set video on every Sunday, and it usually consists of 10 solved problems on different topics of physics. We generally upload the question paper on our Facebook page a little earlier so that you can try to solve the questions and match your answers when the solutions are uploaded. Now one thing, whenever you upload a video, we distribute it into different relatable playlists. So go through the playlist and you will be able to get videos as per your choice, and keep a track of our community post as well. It will help you to make your base strong. Now without any further delay, let's start today's set video. So this is set 24, and this set contains questions from atomic and molecular physics, and we will be discussing the questions and its solution one by one. The first question reads: the ground state electronic configuration of 22 titanium is argon 3d24s2. Which state in the standard spectroscopic notations is not possible in this configuration? Now to solve the question, what we are given? We are given the electronic configuration of this atom. The spectroscopic term for D2, this is D2 because this is filled, so this one is unfilled or empty. Only 2 electrons have been filled, so the spectroscopic term will be determined by these electrons. So D2 so this is equivalent electrons. Whenever you will see such cases, then these electrons are called equivalent electrons. So 2 electrons are there, so L1 equals to 2, L2 equals to 2, and correspondingly the capital L will be equals to mod of L1 minus L2 to mod of L1 plus L2. So L1 minus L2 is 0 and L1 plus L2 equal to 4. So 0 to 4, you will get values between 0 to 4, 0, 1, 2, 3, 4. Similarly for S, both the electrons have spins S1, S2 equals to half. So half, the value of S will be from will be from mod of S1 minus S2 to mod of S1 plus S2. So S1 minus S2 equal to 0 and S1 plus S2 equals to 1. So S equal to 0 and 1. And as you can see, if L equals to 0, 1, 2, 3, 4, then the angular quantum number or term becomes SPDFG correspondingly. Now for these type of problems, for this type of equivalent electrons problem, we should remember this rule: even S will combine with even L, and odd S will combine with odd L. And so the same thing we have done here. So S equal to 0 and L equal to 4. So we have chosen this: S equal to 0, L equal to 2, S equal to 0, L equal to 0. 0 should be considered as some even thing. Okay, so these three things are S equal to 0, L equal to 4. So even S, even L, even S, even L, even S, even L. And in the second case we do odd S, odd L, odd S, odd L, and accordingly we will get J values. How do we calculate J value? J value is calculated in the same way: L minus S to L plus S. The in between all the values will be considered as J values. So for this case also, look, S equal to 1, L equal to 3. So J equals to 3 minus 1 to 3 plus 1. So 2, 3, 4. So accordingly we got these many spectroscopic terms. And when we look at the options, we see that only 1F3 is not coming according to our calculation. So 1F3 is not possible in this configuration. So 1F3 means option 1 is the correct option. Moving on to question number 2. This is from Zeeman Effect. In a normal Zeeman Effect experiment using a magnetic field of strength 0.3 Tesla, the splitting between the components of a 660 nanometer spectral line is. Let's look at the solution. So separation between the Zeeman components is given by delta nu equals to EB by 4 pi m, where E is the electronic charge, B is the magnetic field m is the mass of electron. Now we have to calculate in terms of wavelength, means we have to convert this nu into lambda. So lambda equals to c by nu, means delta lambda equals to minus c by nu square delta nu. So we are taking mod, so we can neglect this negative sign, and what we are doing, we have to calculate the splitting in terms of wavelength. So delta lambda equals to lambda square by c into delta nu. Now everything is given in the question, so we can easily calculate it. So we are getting 6.09 picometer, and it is matching with option 4. So option 4 is the correct option. Now coming to question number 3. The separation between the energy levels of a 2-level atom is 2 electron volt. Suppose that 4 into 10 to the power 20 atoms are in the ground state and 7 into 10 to the power 20 atoms are pumped into the excited state just before lasing starts. How much energy will be released in a single laser pulse? So these are the two energy levels, E0 and E1, and the corresponding atoms are shown here. 4 into 10 to the power 20 atoms, and here 7 into 10 to the power 20 atoms. Therefore the total number of atoms is n equals to n2 plus n1. Now effective number of atoms contributing to laser emission is, this is given by n2 minus n by 2. You should remember this formula. This many number of atoms will contribute in lasing action. So we just replace the value of n from here, and we got n2 minus n1 by 2. Therefore these many numbers of atoms will contributing, and each contribution giving h nu. So this term into h nu will give you the total energy released in a single pulse. So we just replace the values of n2 n1 h nu, and h nu in place of h nu will put 2 electron volt, because the separation between them is given in terms of electron volt. So we can easily convert it into joule by multiplying it with the electronic charge, 1.6 into 10 to the power minus 19. Therefore we will get energy released in a single pulse to be 48 joule, and it is matching with option 4. So option 4 is the correct option. Moving on to question number 4. The LS configurations of the ground state of 12 magnesium, 13 aluminium, 17 chlorine and 18 argon are respectively. So to calculate ground state, we should know the electronic configuration, and from the electronic configuration we should consider the last term. Even if it is even, then it has, if it has closed subcell, then the ground state term will be 1s0. Otherwise, if it has some odd number of electrons at the last subcell, then we have to use this kind of thing. So for 12 magnesium and 18 argon, we see this, the last subcell is closed subcell. So the terms which we'll get from these two things are 1s0. Now for so the problem of 12 magnesium and 18 argon is solved. Now the remaining one is 13 aluminium, 17 chlorine. So let's look at the electronic configuration of those two atoms. So 13 aluminium, we get 1s2, 2s2, 2p6, 3s2, 3p1. So one electron in the p subcell. So you know that p has 3 subcells, so one electron will fill here. So this is less than half filled, and for less than half filled, the corresponding J becomes L minus S. Now how do we calculate L? L is the sum of ML and S is the sum of MS. So 1 means 1, MS means 1 electron is there, so it's half. So L minus S equals to 1 minus half equal to half. So the ground state for aluminium, 13 aluminium is, here you put multiplicity. Now S equal to half, so 2S plus 1 means 2 into half plus 1 means 2, and L means here 1, so SP, so it's P, and J, here you put J values, so half. So this is the ground state for 13 aluminium. In the same way we calculate it for 17 chlorine, but at the last subcell it has 5 electrons. So first, according to the Hund rules, 1 electron will occupy at a time, not according to the rule, some rule is there that electron will fill fast with single electron, then they will make pair. So first one electron, 3 electron is covered. Now fourth one, fifth one will be fitted into this subshell with opposite spin. So 5, so L equal to sum of ml equals to, from we have 2 plus 0 minus 1, so 1, and S equal to sum of ms equal to, so this is producing 0, this is also producing 0, but this will produce half, so we are getting sum of S equal to half. Therefore J, if it is more than, you can see it is more than half filled, and in case of more than half filled situation, the J to calculate ground state will be given by the addition of L and S. So J equal to mod of L plus S means 1 plus half equal to 3 by 2. Therefore the ground state multiplicity 2S plus 1 means 2, L means 1, P, and J is 3 by 2. Therefore the LS configuration of the ground state of 12 Mg, 13 aluminum, 17 chlorine and 18 argon are 1s0, 2p half, 2p 3 by 2 and 1s0 respectively. And for your convenience, I have give you this formula which you have used in this problem. So ground state term J, if the last this subcell is less than half filled, then J will be equal to my L minus S. If more than half filled, then J equal to L plus S, and if it is half filled, then J equal to S. So it is matching with option 3. So option 3 is the correct option. Moving on to question number 5. For a two-level system, the populations of atoms in the upper and lower levels is 3 into 10 to the power 18 and 0.7 into 10 to the power 18 respectively. If the coefficient of stimulated emission is 3 into 10 to the power 5 meter cube per watt second cube, and the energy density is 9.0 joule per meter cube Hz, the rate of stimulated emission will be. Now this is given, the coefficient of stimulated emission B21 equal to 3 into 10 to the power 5 meter cube per watt second cube. Energy density U nu equals to 9 joule per meter cube Hz. Therefore rate of stimulated emission dN2 by d2, dN2 by dt means that is equals to N2 into B21 into U nu. This is the formula for rate of stimulated emission. Now everything is given. N2 is given 3 into 10 to the power 18. Then B21 is also given. B21 is 0.9 into B21 means 3 into 10 to the power 5, and U nu is given to be 9. So rate means second inverse. So it is producing 8.1 into the power 24 second inverse. So it is matching with option 2. Option 2 is the correct option. Moving to question number 6. A diatomic molecule has vibrational states with energies EV equals to h cut omega V plus half, and rotational states with energy EJ equals to B into J plus 1, where V and J are non-negative integers. Consider the transitions in which both the initial and final states are restricted to V less equal to 1 and J less equal to 2, and subject to the selection rules delta V equals to plus minus 1 and delta J equal to plus minus 1. Then the largest allowed energy of transition is, now it is given EV equals to h cut omega V plus half and EJ equals to B into J plus 1, and these are the conditions we are given. So from this condition we see nu V is less equal to 1, so it can be 0 or 1, and for J is less equal to 2, it can be 0, 1 or 2. The possible transitions in which both the initial and final states are restricted to V less equal to 1 and J less equal to 2 are V equals to 0 to 1 and J equals to 0 to 1, J from 1 to J equals to 2. So these are the transitions are possible using this restriction. Now we have to consider the largest allowed energy. So we will only consider this term because this is the only possibility. So we have to consider this, and the largest contribution of energy will come from this transition. So we will consider only these two transitions. Therefore, the maximum allowed energy of transition will be corresponding to this. That's what I have told. Now energy is given by h cut omega into V plus half plus B into J plus 1. Therefore delta E means the energy of transition equals to, it is coming from 0 to 1, so first we will put 1, so h cut into 1 plus half and h cut minus h cut omega into 0 plus half. So this is for vibrational things, and for rotational thing we have to put j equals to 2 first, so b into 2 into 2 plus 1 minus b into j 1 into 1 plus 1, because this 1 is here, and by doing that we will get h cut omega plus 4b, and it is matching with option 3. So option 3 is the correct option. Moving on to question number 7. A helium neon laser operates by using two energy levels of neon separated by 2.26 electron volt under the steady state conditions of optical pumping the equivalent temperature of the system, at which the ratio of the number of atoms in the upper state to that in the lower state will be 1 by 20 is approximately, the Boltzmann constant is given to be equals to 8.6 into 10 to the minus 5 electron volt per Kelvin. Now, according to Boltzmann constant distribution, we know n equals to n0 n naught e to the power minus e by kBt. Number of atoms in the ground state n1 equals to n0 e to the power minus e1 by kBt, because we have just replaced e by e1 and other terms are remaining constant for this case. Number of atoms in upper state n2 equals to n0 e to the power minus e2 by kBt. We are not changing the temperature, so temperature is remaining same for both these states. Therefore n2 by n1 equals to e to the power minus e2 by e1 by kBt equals to 1 by 20. This is given, and we have to find out the temperature of the system. So from this formula we get temperature T equals to e2 minus e1 by kb ln 20. So E2 equal to E2 minus E1 is given to be 2.26. So 2.26 electron volt. Kb equals to 8.6 into 10 to the minus 5 electron volt per Kelvin. That's the significance of giving Kb in terms of electron volt per Kelvin. And ln 20 has value 2.996, and it is producing around 10 to the 8.77 to 10 to the power 3 Kelvin, and it is approximately 10 to the power 4 Kelvin. Because we have to find out the nearest option every time, and it is 10 to the 4 Kelvin, means the fourth option. So fourth option is the correct option. Moving on, question number 8. Of the following term symbols of the NP2 atomic configuration, one is 0, 3p0, 3p1, 3p2 on D2, which is the ground state? Now, before solving this question, I would like to state the Hund's rule again. Why I am using this term again? Because you have already published a set video on atomic and molecular physics. I will be giving you the link in the description. You can check it out. And this is the second set video on atomic and molecular physics. And in the previous video also, I have given you the Hund's rule. This is the same thing. Term with largest multiplicity will lie lowest. Of the term with given multiplicity, this is the multiplicity, that with largest L value lies lowest. In multiplets of equivalent electrons in less than half filled subcell, the level with lowest J lies lowest. This is normal order. Lowest J lies lowest. So this is normal. For more than half filled subcell, level with highest J lying lowest. So this is inverted. Highest, lowest. Okay, term arising from half filled subcell show only very slight fine structure splitting. The lowest term arising from half filled subcell are S terms and are stable. So in this problem we have electron distribution NP2, means 2 electrons 1 2, and we will use Hund's rule. The first thing, so we are just sorting out. First we will consider the first Hund's rule, term with largest multiplicity. So largest multiplicity is 3, so this will lie lowest, so that these two terms are discarded. Only we are left with 3 options, 3p0, 3p1, 3p2. Next Hund's rule says if the multiplicities are same but L values are different, then the largest L value will lie lowest. But here we see the L values are also same, so we will move towards the third criteria. In multiplets of equivalent electrons in less than half filled subcell, the level with lowest J lies lowest. Now which of these J's are lying lowest? So 0, basically 0, 1, 2 is there, so 0 is lying, 0 is the lowest digit, so this 3p0 will lie lowest, means 3p0 will be the ground state, and it is matching with option 1. So option 1 is the correct option. Question number 9. An atomic transition 1p to 1s in a magnetic field 1 Tesla shows Zeeman splitting. Given that the Bohr magneton mu b equals to 9.27 into 10 to the 1 minus 24 joule per Tesla, and the wavelength corresponding to the transition is 250 nanometer, the separation in the Zeeman spectral lines is approximately. So this is the transition 1p to 1s under magnetic field, and this will show normal Zeeman effect. How do we know that it will show normal Zeeman effect? Because you can see the multiplicity of 1, so s equal to 0, and whenever the spin is 0 you get normal Zeeman splitting. In general, this normal Zeeman pattern will consist of 3 equidistant spectral lines having energy separation delta equals to mu b into b, and the corresponding wavelength separation can be found out as follows: equal to hc by lambda, means delta equal to minus 1 by lambda square hc into delta lambda. Therefore delta equal to hc by lambda square into delta lambda. Therefore delta lambda equals to lambda square by hc into delta e. Now everything is given, lambda is given, hc we know, mu b is given, b is given, so we just put the values and we got the answer 0.03 nanometer. But as usual it is not matching with any option, so we have to choose the closest possible answer, and the closest possible answer is 0.01 nanometer. So option 1 is the correct option. Question number 10. This is the last question of this set. If the leading anharmonic correction to the energy of the nth vibrational level of a diatomic molecule is minus chi e into n plus half whole square h cut omega with chi equals to 0.001, the total number of energy levels possible is approximately. The energy of the nth vibrational level of a diatomic molecule is En equals to n plus half h cut omega equals to this is the energy of the nth vibrational level of a diatomic molecule. En equals to n plus half h cut omega minus chi e into n plus half whole square h cut omega. So for the highest possible energy level, energy will be maximum. So den by dn equals to 0. Now we are just finding for which value of n the energy will be maximum, and that will be the total number of possible levels. Just take first derivative of this expression, we get n equals to 1 by twice chi e minus half, and chi e is given to be 0.001, so we just put the value of chi e here and we get n maximum equal to 500. Look, with respect to this term half is quite negligible, so we just kept the first term and we got 500, and it is matching with option 1. So option 1 is the correct option, and this is the end. So I have tried my best to provide the solutions in great detail. Irrespective of this, if you have any doubts or confusion, you can comment down below. I will try my best to clarify them, and any kind of suggestions are always welcome. So this is all for today, guys. If you find this video helpful, please give it a thumbs up, and if you are a new visitor of this channel, please subscribe the channel and press the bell icon so that you never miss any update. Keep sharing, keep loving, and keep exploring the wonders of physics. And finally, thanks for watching.